Okay, now here in question 21, we have the following. It says a graph of average resting heart rates is shown below. So we have a graph that shows heart rates. The average resting heart rate of an adult is 72 beats per minute. Let me just highlight it just in case if it's important. But doctors consider resting rates to be between 60 and 100 beats per second. Okay, let me actually be more straight on it. All right, cool. Within normal range. All right, so here we have a graph. Now, how do we read this graph? Well, you got to take a look at the axis. On the x-axis, we have the ages. On the y-axis, we have the heart rates. So this means that a person who's 30 years old has about an average of 72. Who's about 10 years old has an average heart rate of, I don't know, like 90 something. So this is how you read this kind of a graph. You look at x values, you see where it touches the graph, and whatever that y value is, that is the heart rate for that specific age. But let's look at the statements here. It says, which statement about average resting heart rates is not? So we're looking here for not. So let's be careful here. We're looking for not supported by the following graph. All right. So we don't really need that whole explanation. Let me just make this a little bit larger. All right, that's fair. All right, cool. So we want to see which of the following is not supported by the graph. All right, so let's take it one question on one option at a time. So it says a 10-year-old has the same average resting heart rate as a 20-year-old. All right, so let's identify what is the resting heart rate for a 10-year-old. So if we got here at 10, let me do this in red. We're looking at 10 here. And if we go at 10, we will see that for a 10-year-old, if it's a 10-year-old, it has a resting average. It has a resting heart rate. I don't know, 92, somewhere around here. At this point, the Y value for 10, it's about 92. 10-year-old, 92 heart rate. Now let's look at the following. Here it says, let's look at the heart rate of a 20-year-old. So a 20-year-old, it's about right here. And this is exactly here. Notice that they're giving us the actual coordinate point. For a 20-year-old, the heart rate, it's about 72. So for 20-year-old, it has about a 72 heart rate. So now notice here, this sentence is saying that a 10-year-old has the same average resting heart rate as a 20-year-old. But this is false because at a 10-year-old, you have a 92 heart rate, and a 20-year-old, you have a 72 heart rate. This is a false statement. So this is the answer for our question here because we're looking for something that is not. So here we're pretty much looking for false statements. Okay. All right. So now for question 22 here, it says the method of completing the square. So here we're completing the square. All right. So let's actually make this larger because we do have some space here. All right. So we have the method of completing the square was used to solve the equation. Okay. Which equation is a correct step when using this method? And here the method that they're referring to is the method of completing the square. So let's keep that in mind. So now, how do we complete the square? Well, let me rewrite the function. Okay. Before you complete the square, the first thing that you want to see is there any greatest common factor when it comes to this expression here? 2x squared minus 12x plus 6. Notice that you can factor out a 2. And if you factor out a 2, you end up with an x squared minus 6x plus 3 equals 0. Because again, if you distribute, you get the original. 2 times x squared, 2x squared. 2 times negative 6, negative 12x. 2 times 3, that's 6. All right, cool. Why do we do this? Because if we have a 2 outside, we can, in some sense, eliminate it by dividing by 2. Because in here, it will go away, and now we have x squared minus 6x plus 3, and 0 divided by 2 is 0. Okay, so we're getting closer here. Now, the reason why I wanted to do that is when it comes to completing the square, we would like to have the leading coefficient to be equals to 1. So right here, the leading coefficient was equals to 2. That's not okay. Now that we have a leading coefficient that is equals to 1, which pretty much is the number that is in front of x squared, if that number is 1, then we can continue with the process. Now, again, the process of completing the square is to leave all the variables on one side and all the constants on the other. All right, so let's perform that by taking away 3. So now we have x squared minus 6x equals negative 3. And this is, here's completing the square. This is where it starts. So this is where completing the square starts. So now the second step for completing the square is to obtain the number in front of x, which in this case is negative 6, and divide it by 2, which gives you negative 3, and square it. So that's equals to 9. This is a process of completing the square. You get the middle number, which is negative 6, you divide it by 2, which is negative 3, and you square it, which is equals to 9. Now, what we do with this number, let's continue the process here. What we do with this number is that we add that number to both sides. So let's add the number, which is 9. 9 on the left. 9 on the right. Perfect. Let's simplify this a little bit further. Here we have, oops, don't like that color. So we have x squared minus 6x plus 9 equals, what is this? This is equal to 6. All right, perfect. So the whole process of completing the square is that now we can factor this out. We can factor the left side out. We're looking for two numbers that if you multiply, gives you 9. And if you add them up, it gives you negative 6. Here, what we want to do is just factor the left side. So notice that those two numbers are negative 3 and negative 3. Because negative 3 times negative 3 equals positive 9. Negative 3 plus negative 3 gives you negative 6. So that means that we can rewrite this as x minus 3 and x minus 3 equals to 6. But notice that when you write it twice, you can just rewrite it as x minus 3 to the second equal to 6. Now let's stop here and let's look at our options. And notice that we will have obtained here. What we have obtained here, it's exactly option number 1. Okay, so now we're going to take a look into example 23. Now, for example 23, what we have here is the following. It says Nancy works for a company that offers two types of saving plans. Plan A is represented on the graph below. Okay, so we know that plan A, it's on the graph. Now, plan B is represented by the function f of x, this whole function here. F of x equals 0.01 plus 0.05 x squared, where x is the number of weeks. So Nancy wants to have the highest saving plan possible after a year. Okay. And then for some reason, Nancy picks plan A, and we want to know about her decision. Okay. So let's see what's important about here. We got two plans, where plan A is being given by the graph. And plan B is being given by some function here. Okay. So this is our function for plan B. Let's see, how can we tackle this problem? Well, what is the time frame that we're looking at? It really says Nancy wants to have the highest saving plan possible after a year. Okay. So let's see what is the savings after 1 year under both plans. Okay. So at least for plan A. So let's say what we're looking for is we're looking for the savings after 1 year. So if we look at plan A here, plan A, the x-axis is given in weeks. So what we have to do is see how many weeks are in 1 year. So at least for plan A, we're looking for 1 year. 1 year is equal to how many weeks? Well, we know that we have 365 days in a year. Okay, 365. We're looking for weeks, and we know that each week has 7 days. So in a year, there is, I'm just going to say 52. There is about 52.14 weeks. Okay. So now let's see. Under plan A, what is the y value when it comes to 52 weeks? So this is 50. 52, it's going to be somewhere around here. So 50, 1, 2, 3, 4, 5. So that's about right here. So under 52 weeks, we are going to have about 100, I don't know, like about 105, give and take. So notice that under 52 weeks, we're going to have about 102, 105. So what we have in 52 weeks, we have about 105 in savings. Because this is what the graph is telling us. So this is for plan A. So now let's look at plan B. Now, how can we figure out the savings for plan B? Well, they're giving us a function here. Notice that in this function, the only variable is x. And here, x is the number of weeks. All right, so that's great. We know that we're still looking for 52 weeks. So let's look at our function. And we're going to see what happens after 52 weeks. So pretty much what happens when x is 0. X is 52. So we got f52. So here, x is equal to 52 because that's how many weeks we have. So we got 0.01 plus 0.05. And instead of an x, we're going to plug in 52. To the second. And if you do this on your calculator, you are going to end up with f of 52. If you plug this in the calculator, you're going to have 135.21. So what this is saying is that there is $135 in savings. Okay, so at least we know that in plan A, she's going to have $155 in savings. In plan B, she's going to have $135 in savings. All right. So after knowing this information, let's see if we can actually answer her decision. We know that Nancy picks plan B. So now, let's look at her decision. Okay. So Nancy chooses plan B, and her decision is, well, let's just look at here. We know that, at least in plan B, she's having the most savings. In plan A, we have 105. In plan B, we have 135. So if Nancy picks plan B, then her decision is correct because that's where you have the most savings. So we can eliminate the ones that said incorrect. So now it's either 1 or 2. Now let's look at the difference here. It says correct because plan B is an exponential function and will increase at a faster rate. And for option 2 is correct because plan B is a quadratic function and will increase at a faster rate. Okay. Now let's say plan B is being given by the function here. But now notice that in this function, This function, it's an example of a quadratic equation. The reason is because we have a second exponent here. Because the highest exponent is 2, then this is a quadratic function. So that pretty much narrows it down. Yes, it is correct. But she uses plan B because it is a quadratic function and will increase at a faster rate. We know it's a quadratic function because of the second exponent here. Moving on, we have example 24 here. All right, well, let's read the following here. It says, the 2014 winner of the Boston Marathon ran as many as 120 miles per week during the last few weeks of his training for an event. His mileage can be modeled as, okay, so again, we have some kind of a function here. So let's just notice that. Where W, here W, what does W represent? Here W represents, what does W represent? Hold on, let me change this. Here W represents the number of weeks since the training began. Okay. Which statement is true about the model MW? All right, well, let's look at the time here. So notice here that what they're giving us right here is that we want to use this function to come up with the correct option here. But notice that this function is written as MW equals 120.90 equals W minus 1. So at least in here, the domain of the function is W, which pretty much is what we plug in is W, but we know that W represents the number of weeks since the training began. Since the training began. All right, so that means that this function, it's in terms of weeks. This function is in terms of weeks. This function is going to give you how many miles you have run given a certain week. And knowing that, then we can just choose option 3 because this MW represents the total mileage run in a given week. And we know that this is true because the domain of the function is W. What we plug in each function is W. And we know that W represents weeks since the training began. So with that said, option 3 is the correct option here. All right, moving on. Now, let's look at example 25 here, which this is the first question when it comes to the open response. So let's take a look at in here. It says, in an attempting to solve the system of equations, y equals, so we try to solve a system of equations, and we have two equations here. This is our first equation, and this is our second equation here. John graphed the two equations on this graphing calculator. Because he saw one line, John wrote that the answer to the system is the empty set. Is he correct? Okay. What does it mean for you to have an empty set? So an empty set, it means that there is no solution. This is what it means. If your answer, or if you end up saying that, well, my solution is the empty set, that's pretty much saying, hey, I have no solutions. Now, because he's graphing, to have no solutions, it means that the graphs, they do not intersect. Because we know that when you have a system of equations, when you graph them, the solutions are where the graphs are touching each other or they're intercepting. All right, well, let's analyze this more shortly. So let's separate it. Equation 1, it's already solved for y, so that gives us no problem whatsoever. Now here, let's see what happens with equation 2. Equation 2, we have 6x minus 2y. 4. Let's solve for y and see what happens here. So if we want to solve for y, let's eliminate the 6x. This cancels. So notice here that you cannot combine them. So let's just write them next to each other. Perfect. To solve for y, we gotta divide by 2 here. Negative 2, negative 2, negative 2. So this way, this cancels out. And now we have that y is equal to, well, negative 6 divided by negative 2, that is positive 3. So 3x. 4 divided by negative 2, it's negative 2. But notice what's happening here. Notice what's happening here. It says the first equation is written like this. And the second equation, even though it looks different, when you solve for y, it's exactly the same as the second equation. So if you graph both equations, you will see that they're going to overlap. It's going to be one equation. So, and this is just a general case. Let's say you have your solution here. Where's the line here? Okay. So let's say that the first equation, if you actually plug that in, it's going to give you some line that looks like this. So this is for the first equation. Now for the second equation, because it is the same line, because it is the same equation, it's going to give you the same graph. So that means that it's going to overlap. So now, if the graphs are overlapping, they are touching each other infinite amount of times. And every time that they intersect with each other, that is a solution. So he was the student, who's this? John. Was John correct by saying that the solution of the system is an empty set? No, he's not. Because if you graph them, one graph is going to be on top of the other. They are going to intercept many amount of times. So they're going to have actually infinite amount of solutions. So that's exactly our explanation. Is he correct? Explain your answer. So, no. I'm actually going to type this. So no, he's definitely not correct. No, he's not correct. Now, why? Well, pretty much is because the first and second equations are exactly the same. Okay, let me move this over here. The first and the second equation are exactly the same, which suggests, or which pretty much says, saying that there is infinite amount of solutions because they intersect infinite many times. This is pretty much it. So no, this student is not correct. Because if you graph both of them, you will see that it's the same equation. That's why it looks like it's just one solid line, because it will overlap, such as here. So that is pretty much saying that no, they overlap, they're touching each other many infinite amount of times. So no, the answer is not the empty set. Now, let's look at example 26 here. In example 26, It says a typical marathon is 26.2 miles. Alan averages 12 kilometers per hour when running marathons. Okay. Determine how long it will take Alan to complete a marathon to the nearest tenth of an hour, and we're going to justify our answer. So here, you will see that there's a problem with the units here because a typical marathon is 26.2 miles, but notice that what Alan averages is 12 kilometers per hour. So we're going to be comparing miles with kilometers. The first thing that you should do, or we should do, is let's convert 12 kilometers per hour to miles per hour. So the first thing that we want to do is we're going to be converting kilometers, or to be exact, 12 kilometers into miles. So if you look at your reference sheet, you will see that 1 kilometer is equal to 0.62 miles. This is a piece of information that is provided to you on your reference sheet. So knowing this, how many miles there is in 12 kilometers? Well, if 1 mile is 0.62, then that 12 kilometers is equal to 12 times 0.62 miles. So 1 mile is 0.62, so you want 12, well, you multiply 0.62 12 times. So this is saying that 12 kilometers, 12 times 0.62, let's check that out. It's 7.44 miles. Okay, so at least we know that Alan runs at about 7.44 miles per hour. So now, let's see if we can actually answer the question now. Is to determine how long it will take Alan to complete a marathon. Okay. But we know that a typical marathon is 26.2 miles. So we pretty much want to see how long does it take him to complete a marathon. So how many times or how many hours does he need to run in order to cover the typical marathon? So the second thing that we want to do is to find the time. We want to find the time that is needed. All right, let's check that out. We know that it takes approximately 26.2 miles marathon. So we know that a marathon what is it? 26.2? All right. So we have all we need. This is all the information that we need now. Because now we know that the speed is equals to distance over time. But we do know the majority here. We're looking for time. But we know that the speed that he runs because Alan averages 12 kilometers per hour, but we know that 12 kilometers is 74.44 miles. So his speed is 77.44. What is the distance that he needs to travel to finish the marathon? Well, that's 26.2. Do we know the time? Nope. That's exactly what we're looking for. So this is the setup. All we gotta do is just solve for t. So if we want to solve for t, it's always nice to just put over 1. Now that we have it in this form, we can cross multiply here. And if we do so, we're going to have t times 7.44. And if we cross multiply this once more, we're going to have 26.2. I'm sorry for the handwriting. For some reason, the pen is giving up. So we want to solve for t. Let's divide by 7.44. So now we know that the time that it takes him is 26.2 divided by 7.44. And if you do that in the calculator, you will see that it takes him 3.52 hours. Perfect. So, but notice here that it does say round your answers to the nearest tenth of an hour. So it's not 3.52 because we want it to the nearest hour or tenth of an hour. Then the time is just 3.5 hours. And again, I apologize for the pain. I don't know why it's not responding correctly. All right, but this is the final answer here. So now this concludes this section for the Common Core Regions, Algebra 1. In the next video, we will start with problem number 27.